Hello everyone. In this video, we'll take a look at three problems: a problem on water budget, a problem on hydrographs, and a problem on return periods of storms. So the first problem here, we have a watershed basin, a drainage basin, with an area of 10,000 square kilometers. So the area is given. So if we are to look at it from a system perspective, and the drainage basin being the control volume, we can then take a look at the fluxes going into the system and the fluxes leaving the system. So in this case, we have Q. So a stream takes 140 cubic meter per second of water out of the basin. So this is annual value. So this one is per second. So we have Q out. We have precipitation going into the system, and another flux that's leaving the system or the basin here is the evaporation. Now we'd like to find out what actually evaporation is. Something we need to find out, but precipitation is given. We'd like to find out what the evaporation is for one given in 1 year. So to solve this problem, we need to make a couple of assumptions. First one, that there are no other fluxes besides the outflow through stream discharge, the precipitation, and evaporation. The second assumption we make is there is no change in storage over that time period. So let's write our assumptions. So there are no other fluxes. And second assumption is the storage over time is equal to 0. Once we make these assumptions, we can start with our equation for change in storage with time. So that is going to be equal to all the flux into the system, so summation of all the fluxes in. So fluxes, let me just do flux in minus sum of all the fluxes out of the system. So in this case, left hand side is 0. The fluxes into the basin, in this case, is just precipitation, and the fluxes out, we have discharge out, and we have evaporation. We can rearrange the equation, so we express it in terms of E. So E equals P minus Q out. So in this case, if you take a look at the units for P, so we have it in terms of centimeter per year. Q out is in volumetric units. So volumetric unit per time. So we need to keep our units consistent. So let's convert our Q out. So let's just do that here. Q out is, what do we have? 140 meter cube per second. So let's convert that into units of depth per year. So this one here is already in units of centimeters. And better yet, we can convert that into meters. 1.05 meter per year. So this one here is in units of meter per year. So let's take care of the time units first. So in one day we have 86,400 seconds. In 1 year we have 365 days. So that will then convert our units here to per year. Now, since this one already takes into account the entire drainage basin area, so the depth, unit of depth here is the value you would get if you were to spread out the volume over the entire basin. So the area is 10,000 square kilometers, and we need to convert that into square meters. So in 1 kilometer we have 1,000 meters. So if we are to multiply by 1 kilometer over 1,000 meter, all of it is squared, we should get our units consistent with the units of P. Okay, so if we are to calculate this, we'll get a value of 0.4415 meters per year. Now then we can go back to our equation for evaporation. E then equals, so we have precipitation of 1.05 meter per year minus Q out, which is 0.4415 meter per year. That'll give us evaporation of 0.61 meter per year. So in the second problem, we are given a 2-hour unit hydrograph. So a unit excess rainfall occurs during a 2-hour window. In Wright Water Creek watershed, so this one here is a unit hydrograph. 2-hour unit hydrograph. So the 2-hour here is the duration of the storm, but still it has, the unit here is the amount of excess rainfall. So this one pertains to the excess rainfall, and the 2-hour pertains to the duration of the storm. So we are given a 3-hour storm, a 6-hour storm, and within that 6 hours, during the first 3 hours, first 2 hours we have rainfall of 3 inches. In the next 2 hours we have rainfall of 1.5 inches, and in the last 2 hours we have rainfall of, actually, so in the In the second 2 hours we have rainfall of 4.5 inches, and in the last 2 hours we have rainfall of 1.5 inches. Among of the rainfall, 2/3 turns into runoff. So when it comes to hydrograph, we're concerned about just the runoff, what gets infiltrated into the soil or what gets stored in other forms. We do not want that when we work with hydrograph. So let's see what the runoff is for each of these three storm portions. So for the first 2 hours you have 3 inches, so 2/3 of that is equal to 2 inches. So that's the runoff for the first 2 hours. For the second 2 hour portion, we have rainfall of 4.5 inches, and 2/3 of that is equal to 3 inches. Finally, for the last 2 hour storm portion, we have rainfall of 1.5 inches, and 2/3 of that equals 1 inch. So now we have the runoff for the three portions of that 6 hour storm event. Now again, just to get an idea or think of it graphically, if this one here is your unit hydrograph, so plot that in green. Oops. Okay. Let's say if you were to plot that hydrograph, it looks something like this. You have time on the x-axis and discharge on the y-axis. And this is unit hydrograph itself. You see here at time t equals 0, you have discharge of 0 as well. So if this was the unit hydrograph for 2 inches runoff, you would get discharge that would be double of the unit hydrograph. So you'd get something, let's say like this. So that is how it would affect for runoff that is not of unit quantity. So in this case we have 3 different contributions from the 3 storm events, so to say, and we want to add the contributions from these 3 different sections of the storm over that 6 hour window and get our net runoff for that entire 6 hour duration. So to find the contribution from the first 2 hours, we can do 2 times unit hydrograph, and it will have the same units of cubic feet per second. So 0 for the for time 0. For 1 hour we have 600, 1600, 2400, 2000, 1400, 800, 400, and 0 for end of the 7th hour there, or end of the 8th hour. Similarly, the contribution from the next 2 hour rainfall, So we have 3 inches of excess rainfall, so 3 times unit hydrograph. But the effect or the contribution of that second 2-hour rainfall is not going to be seen until after the end of first 2 hours, right? So there's going to be a lag of 2 hours before the contribution from the second 2-hour portion of that storm is observed. So no contribution there, no contribution there, and we'll start seeing contribution from hour 2 here. So 3 times 0 is 0. 3 times 300 is 900. So draw some lines so I keep track of the time. 8324. 12 times 3, 3600. So 3000. 2100. 1200. 600, and finally 0. So at this point we are pushing this 2 hours beyond our unit hydrograph. So 9, 10. Now the contribution from the last 2 hours of that storm. So this one has the same units, CFS 1 times unit hydrograph. The contribution from the last 2 hours of the storm is not going to be seen until after the end of 4 hours. So we see no contribution the first 2 hours or the second 2 hours, and then we'll start seeing the effects from the 1 inch excess rainfall. 0, 300, 800, 1200, 1000, 700, 400, 200, and finally 0. So we're adding yet again 2 more hours into the unit hydrograph. So 11, 12. Okay. So now we have the contribution from the 3 portions of the storm. We can add those up, or we can add the contributions from those 3 storm events and get the cumulative direct runoff hydrograph. So extend all the way. Okay. So 0, 600. So there's no contribution from the second or third 2 hour storm events. 1600, and similarly we can fill out the rest. So let me do that. Okay. So I've added the contribution from those 3 storm events. What we also have is a constant base flow of 50 cubic feet per second. So base flow, so it's the same 50, same value at any given time. So the total runoff hydrograph, then is going to be the sum of the base flow and the contribution from the runoff. So 50 for time 0, 650, 1650, 3350, 4450, 5350, 4650, 3750, 2250, 1350, 450, 250, and when the effect of those storm events wane, you're only left with base flow again. So at the end you have 50. So this then is your solution. Okay, let's take a look at our final problem. So we have a storm, the duration of 40 minutes and intensity of 3 inches per hour. Let's just add a line here to help me guide. Okay, and another line. Actually, I don't even need that. Okay, anyways, so 40 minutes and 3 hours. So we're actually just following, just follow the line that's already given here. But if it was in between two different values, okay, let me see what happened here. "40 minutes, well, I didn't have to do this, but there you go. Wherever it intersects, that is the curve we're interested in. So in this case, it's the 10-year average frequency, or the storm with a 10-year average frequency that the 40-minute duration and intensity of 3 inches per hour is describing. So the return period in this case then is ten years. The probability of a storm of that, or the probability of that type of storm happening is then equal to 1 over R, the return period, and that is 0.1, or that is 10%. So we'll just follow the ratio for the rest of this problem. Now the question is asking the probability of a storm of at least that return period occurring the next year. So let's call that question 1. Question 2 is the probability of the storm being equal or exceeded in both of the 2 years. So that's our second problem. The third is at least is the probability of an event of at least that magnitude occurring, well, at least once in the next 2 years. So it could occur in the first year, not occur in the second year, not occur in the first year, but occur in the second year, or occurs in both of those 2 years. And finally, we'd like to find out the probability of this not occurring at all in the next 2 years. So it doesn't occur in the first year, it doesn't occur in the second year. So for the first part, the answer is just going to be the p-value we just calculated. So let me just do that. P1 equals 0.1. The probability for case 2, so it is exceeded or equal in the first year, so 0.1, and so in probability, and is multiplication, so it's equal or exceeded also in the second year, so that'll give us 0.01 for case 2. And that equals 1%. Okay, so for case 3, we can do it in one of two ways. So equals or exceeds in both of the so hold on, it's the third one here. So equals or exceeds at least once in the next 2 years. So one way that would happen is it does equal or exceed in the first year, but not in the second year. So this is the probability of such an event not exceeding or equaled in any given year. Or the other way this could happen, so or is addition in probability. So the first year it doesn't equal or exceed, but it exceeds or equals in the second year. The third way we could also have this happen is it equals or exceeds in the first year and equals or exceeds in the second year. And this one here, so 0.1 times 0.9, 0.09. So this is identical, so we can just multiply that by 2 plus 0.01, 0.18 plus 0.01, that equals 0.19. For case 4, such a storm event doesn't occur in the first year and doesn't occur in the second year, which we are describing is something we was a part of our previous problem. So the probability of it not occurring, actually that is not it. So probability of that not occurring in the first year, so 1 minus 0.1, and not occurring in the second year. So this one here is 0.9 times 0.9, so that gives us a probability of 0.81 or 81% of such a storm not occurring in both of the 2 years. And one thing I actually wanted to just go back, there's another way for doing case 3. So you can also look at the probability of such a storm event occurring at least once in the next 2 years is equal to 1 minus the probability of it occurring in both those years, right? So 1 minus 0. So not occurring in the first year, 1 minus 0.1, and 1 minus 0.1. So this gives us, so P3, 1 minus 0.9 times 0.9 equals 1 minus 0.81 equals 0.19. So either way, you can get the answer. So that is it for this video. I'll see you guys in the next video.